The idea was the following. This is the error function, W1, W2, Wj, and R. That is equal to the solution I is from 1 to n. And it is the total number of data points. And then solution J is from 1 to k, Wj, e raised to the power minus R xi minus mu j whole square minus yi square. So that was the error function in RBF networks. Given the value of R, if R is specified as 1, given any value of R, this whole thing is simply linear regression. Okay? With this corresponding to the transform feature. Make sense? So you might last time this formula, it can be viewed as transforming the feature vector xi to new feature vector, that we call it xi bar. And this particular is the jth component of this vector. Make sense? So if R is specified, then this simply replaces the linear regression original feature vector with another feature vector. और जैसा कि आपको पता है नॉर्मली अगर हम फीचर वेक्टर को ट्रांसफॉर्म करते हैं, बल्कि हमने ये भी देखा था कि अगर हमने 2D की पॉलिनोमियल फिट करना है तो वी कैन हैव पर्टिकुलर फीचर ट्रांसफॉर्मेशन, उसके बाद अगर हम लीनियर रिग्रेशन लीनियर मॉडल भी फिट करें, दैट एक्चुअली कॉरस्पॉन्ड्स टू अ 2D पॉलिनोमियल in the original space. So this is also one type of feature transformation is happening. It is not a polynomial feature transformation, it is some type of feature transformation. And after the transformation of the feature, the linear regression is happening in this case, which means in the new feature space, in the transformed feature space, there is a hyperplane that is separating, and in the original feature space, there is some non-linear complicated boundary, which is the Gaussian surface. Make sense? But the implementation, given the value of R, is straightforward. Once you have R, this is simply linear regression and nothing else. Now, when you apply kernel, not just the RBF kernel, any kernel, it is worth noting that the parameters of the kernel, the accuracy sometimes is very sensitive to the tuning of those parameters with respect to your data. आपका जो भी data है, kernel के जो particular parameters हैं, if you tune them accordingly, you may have a significant improvement in your accuracy by just tuning the parameters accordingly. So these kernel parameters in this particular case, the value of R is not just something that you carelessly choose or let me fix R is equal to 1, you just live with it. If you tune it accordingly, you may observe a very significant jump in accuracy. So this R should be chosen carefully. In this particular case, because R is the parameter of the kernel. If you're using some other kernel, it will be having its own parameters, and those parameters should be chosen carefully. Yes? Now, one way in this particular case is we may end up choosing this R using a cross validation. So let's starting R from there and then move R this and that. We may apply cross validation like we do most of the time, and we select one which performs the best. But in this particular case, this value of R can be chosen very systematically. All we need to know is what parameters W and what value of R actually minimizes this error in total. Make sense? If we fix R to some random value, then we can solve this equation after fixing R through linear regression. And linear regression will give us W vector. Yes? W1, W2 and stuff. WKS. Make sense? Now, if we use R is equal to 1, then linear regression gives us this W, which means with R is equal to 1, these are the parameters that minimizes the error. Make sense? But using this W, with fixing this W, we can find out another R which is other than 1, and it may decrease the error further, because our goal is to minimize this error. Make sense? So this kind of back and forth algorithm algorithm, expectation maximization algorithm, has the following form. You fix some value of R and then find out the W through linear regression. Then fix this W and find out R through gradient descent. Once your W is fixed, W is treated as constant, this whole function has only one variable or parameter, which is R. So you can find out the best R that minimizes this function given the W is available. And then R can be found if the derivative of this error with respect to R is equal to 0. But in this particular case, the derivative with respect to 0 cannot be found in a closed form way, so you apply gradient descent on R. That would be a very fast gradient descent, only one variable, you can quickly converge. Once you find out the very best R, then you can fix that R and you can apply the linear regression again and find out the W that minimizes the error further. So this back and forth, I mean, you keep on applying this until you get no significant improvement in the error. And at the end of the day, you'll be having W and R that minimizes this error function. Make sense?
Yes.
Yes, sir. So this kind of algorithm is known as EM algorithm that does this. And this is kind of automatic tuning of this parameter also, a systematic tuning of this. We do not need a cross-validation. We do not need a jump that's specified by the user, but it takes care of what should be the best value. Make sense? The third thing about this is we do not, in this particular framework, we do not use regularizer instead. And the reason is the RBF kernel in this particular setting, they are self-regularized and we do not need the regularization as a separate component. Actually, the theory of regularization, it arrives, it gives result to these RBF kernels and stuff. So in this particular setting, we do not need a regularizer upon which we want to cross-validate. Yes, but the cross-validation will happen before, the cross-validation will happen, may happen on the selection of the number of groups. So you know, the one thing that we assume pre-hand is let's partition our data, let's cluster our data into k groups. And that value of k, you may have the value of k different and you get a different performance. So you may cluster your data into 2 groups and then find out the performance, and then 3 groups and find out the performance, and so on. So rather than cross-validating on the regularizer parameter, which in this case is not there, regularization on the cluster, number of clusters, might be a good idea. Make sense? So the whole algorithm is select the number of clusters, cluster your data, find out the centers, and then apply this EM algorithm back and forth and find out W and R. Make sense? And this algorithm is simple in the sense that, and it has in practice, the results of this RBF network is actually in practice is comparable with SVM using RBF kernel. So if you use SVM using RBF kernel, SVM with RBF kernel, and RBF network classifier, in practice they have quite a similar performance. If the tuning happened very well with kernel parameters and stuff. But it is worth noting that if you have number of data points very large, number of data points so large, which is a good thing to have. Having a lot of training data is a good thing to have. If your training data is very large, your SVM quadratic programming solver will take a lot of time to converge. In contrast, this kind of linear regression will be very quick and converge with a lot of data points. So I do not recommend that you replace SVM using this, but in certain situations, you may end up, where SVM is taking very long to converge and to find out the optima, you may consider this classifier in your toolbox as equivalent kind of replacement, if not exactly. Make sense? Okay. So far we have seen a lot of blessings of dimensionality increase. In the very first class and in the next class and so on, we see, okay, let's apply a 1-degree polynomial which is just a hyperplane through the feature space. And if the accuracy is not very well on the validation set, we may end up complicating the model. And complicating the model means let's apply a 2-degree polynomial, for example, which in turns is equal to increasing the dimensionality of your feature space, coming up with the new features, transform to poly if you remember that function. Come up with a new set of features which actually increases the dimension of your feature space and came up with a new set of features, and then we apply a hyperplane which may end up having good accuracy. And in some cases, in particular the data set में आपको OCR का दिया था 26 classes का, people have reported that the 3-degree polynomial results are better than 1-degree polynomial in that case, which means increasing the dimension of the data, which actually applying a 3-degree polynomial effectively means you increase the dimension of the data and then you apply a linear discriminant. Make sense? Increasing the dimension in that case was helpful. Make sense? In some cases, in fact, if your raw feature space is very high, the total number of features you are given, they're very high, and the number of data points are relatively small, then, I mean, forget about increasing the dimensions further. Even if you apply some discriminant or some classifier in those dimensions where the total number of data points is small, may end up having very bad results.
Yeah.
Due to the problem of overfitting, and sometimes some useless kind of features are there, some uninformative kind of features are there. So sometimes it is helpful to reduce the dimension to improve the accuracy, and to throw away the features that has no information at all with respect to the classification and with respect to the representation of the data. Make sense? So this is good to know that sometimes we can increase the dimension and we can get good results, but sometimes the exact reverse actually is working. So you have a lot of dimensions and then you reduce dimensions and then you get a lot of improvement, and that will happen if you have, in particular case, if you have small sample size problem. Small sample size problem means your feature space is high, your number of data points is small. In that case, almost always of the time you reduce your dimensions and you do the stuff. Make sense? So today I will discuss one dimensionality reduction technique, and in the very next lecture I will discuss another famous dimensionality reduction technique. So that we know how to decrease dimensions, and sometimes decreasing these dimensions can actually improve the accuracy. Make sense? And handling of the data as a side effect, less memory and all that kind of stuff. Question? By the way, before starting the dimensionality reduction, the idea of dimensionality reduction is intuitively, can be followed in a following way. Let's say you have 100 features, just an example. Let's say you have 100 features, yes? And you have, let's say, 85 data points of 2 classes, 3 classes, whatever. Let's say you have 100 features. Okay. If all the features are useful, each and every feature, for example, the first feature, the second feature, you have 100 of those. If all of them are useful, you obviously should not throw any of those, you should not select a subset of it. You should use all of them. But almost all of the time when your dimensionality is high, total number of data points is small, some of the features they are less useful or even no useful. And throwing those away makes two things. If somebody tells you that out of these 100 features, there are 4 features that are the best and they have almost all the information that all 100 have. Make sense? And if you somehow get to know those 4 features, okay, feature number 59, feature number 65, feature number this and that, these 4 features, they actually contain a lot of information. The rest of the features, they are just useless. Then using just those 4 features and fitting a plane or whatever, you actually reduce a lot of code that was happening due to high dimensions. Make sense? So this is just, knowing that some of the features are useless, throwing them away is actually good, because less number of dimensions of the data, less chances of overfitting is there. Make sense? And memory handling, side effects are there. If a lot of them are useful, no one of them is useless, and you end up using all of them. But in most of the practical cases, many of the features given to you. याद रखें जो हम क्लास यहाँ पे शुरू से ही हम पढ़ रहे हैं, we never actually go and extract the useful features. हम हमेशा आप में से अक्सर लोग मशीन लर्निंग रिपोजिटरी से डेटा डाउनलोड कर रहे हैं, कुछ अपने प्रॉब्लम्स पे काम कर रहे हैं, तो वो अगर इमेजेस पे काम कर रहे हैं, OCR पे काम कर रहे हैं, फेसेस पे काम कर रहे हैं, तो दे क्रॉप एन इमेज इंटेंसिटी फीचर्स लेके आ जाते हैं without actually considering a feature 1 is important, feature 2 is important, feature 3 is important. So we work with raw features और अभी तक हम ऐसा ही कर रहे हैं. What if we came up with the features that are good for discrimination or good for reconstruction and stuff like that? What if we go and pre-process our features before actually applying the classification? Make sense? So अब तक हमने ऐसा किया नहीं है. सही है जी? अगर हम ऐसा करें तो classification accuracy tend to improve. मेरी बात समझ में आ रही है? Okay. One way is कि आपको जो raw features दिए गए हैं, let's say कि उसमें कुछ features ऐसे हैं which are very important with respect to the final goal, the classification. कुछ features ऐसे हैं. Let's say 10 features. Let's say मैं आपको बता देता हूँ 10 features. सही है? Now which 10? Let's say the 100 features are there, and let's say somebody told you that there are 10 features that are the best, the rest 90 of the features can be thrown out, and even सिर्फ ये नहीं कि उनको थ्रो करके accuracy same रहेगी, accuracy actually improve हो जाएगी because you have reduced the dimensions, overfitting चलेगी वगैरह and stuff.
Nice.
सही है जी? So how can we select the 10 features? अगर मुझे ये पता हो कि 10 features हैं जो सबसे अच्छे हैं. Average features के लिए लें.
किसी फीचर्स की एवरेज हाई होगी तो हमारे पास मोस्ट इंपोर्टेंट होगा.
फीचर की एवरेज हाई होगी.
दैट वाज ए फीचर था
लेकिन आपने डेटा को स्टैंडर्डाइज कर दिया होगा ना ऑलरेडी. डेटा को मीन सबट्रैक्ट कर दिया हुआ है, नॉर्मलाइज कर दिया हुआ है 0 से 1 के दरमियान. सारे फीचर्स का एवरेज 0 है, सारे फीचर्स की स्केल 0 से 1. इट इज एक्चुअली द एंड गोल. जो क्लासिफिकेशन है वो हमें बताएगी कि कौन सा फीचर देता है. मिसाल के तौर पे अगर कोई मुझे बता दे कि यार सिर्फ एक फीचर आउट ऑफ दीज 100 फीचर, जस्ट वन फीचर इज देयर which is the most important feature, all the other 99 features can be thrown out, just one feature. I do not know which one of these, but exactly one feature is the most important feature. Then how should I go? Sorry?
One by one.
Yes, so try out the first feature, then afterwards you have full classification framework, just use that feature and see what is the error on the test set or the validation set if I use just one feature. Use the first feature, compute the validation error, use the second feature, compute the validation error, and so on. It is kind of a cross-validation wrapper around. Use one feature, which one to use. Now you use the one feature which is the best. Make sense? Now if somebody asks, say you, okay, if I'm going to use one feature, then feature number 59 is the best, let's say. Say it. What if the person just say, oh, sorry, actually, there are two features that are the best. So which two? After having known that the feature number 59 is the best, if I tend to use only one feature, if I have to use two features and I know that feature number 59 is the best if used alone, then how to select the second feature?
59 तो लोग कर देंगे बाकी कॉम्बिनेशन में साथ.
So one idea जो कि स्टार्ट में बिल्कुल बड़ा इंट्यूटिव लगता है कि आप 59 के साथ 1 को मिलाएं. सही है. और वैलिडेशन. So now you have two features, 59th feature and the first feature. Yes? So total number of features are 2 now. And then compute the validation error. Then 59th के साथ second को मिलाएं. 59th. So there are how many combinations are there? I guess 99 combinations. Yes, 99 pairings. 59 को अगर fix करने there are 99 pairings. Then come up with the best. Make sense? There is a paper by variable selection. टाइटल उसका रफली है वेरिएबल सिलेक्शन. इसके आगे पीछे भी कुछ आ रहा है. ये आइजाबेली गोयोन का पेपर है 2003 का. शी इज द ऑथर. आइजाबेली गोयोन 2003 का ये पेपर है. इस पेपर को तफसील से पढ़ेगा तो वेरिएबल सिलेक्शन या फीचर सिलेक्शन के ऊपर इसने मुफस्सल बहस की हुई है. इस पे इसने बताया है कि इनफैक्ट if you come up with, for example, two features than fixing one which is the best and then pairing another with it. There is another pair of the features in which no one of the feature is the best as single and that pair outperforms.
अच्छा
मेरी बात समझ में आ रही है? Or is possible? Actually, she has proven it in all that paper. Make sense? So you should go through that paper and give them examples. This is the example. अगर मैं एक best feature select करूँ, this is the best feature. But अगर मैंने दो select करने हो तो these two are the features that are performing the well. But इन दोनों में से कोई एक भी best नहीं है. अगर single से use किया जाए. Make sense? And there the problem becomes very, very hard because now you have to see all the subsets of 2.
Yes. And choose 2.
And choose 2. और अगर कोई बता दे कि 3 फीचर बेस्ट हैं
And choose 3.
तो ये यानी कि ऑप्टिमल रिजल्ट नहीं, ये नहीं है कि आपने जो पेयर बेस्ट सेलेक्ट कर लिया उसके साथ तीसरा ज्वाइन कर लिया. The global result will come, you try all triples. Make sense? And so the variable selection, और ये भी तब है जब आपको किसी ने बता दिया कि choose these many features. अगर आपने ये भी find out करना है कि how many features to select. अगर आपने ये भी देखना है कि हो सकता है 10 features सबसे अच्छे काम करें, हो सकता है 15 features सबसे अच्छे. Then you have to check all possible features of size 1, all possible subsets of size 2, all possible subsets of size 3, and do all that stuff, and at the end of the day find out the subset that performs the best on your validation set. Make sense? And this problem is exponentially hard because the total number of subsets of a set is exponential. Make sense?
Yes.
So if your dimensions are high, variable selection is not recommended. Variable selection is not recommended. और अगर dimension पहले से ही कम है तो फिर आप मज़ीद क्या selection करते हैं? Actually, the problem is you have a lot of dimensions, so do not go towards variable selection. If your goal is to come up with the features that perform absolutely well. ये जो मैं बात भी बता रहा हूँ, best feature ले लें, उसके साथ एक join कर लें. These are approximations. These are approximation heuristics that work. But they do not give, and they do not tend to give. You cannot prove that they give the best results, and you cannot find out the best results in time because these are exponential checks to find out. Make sense?
Makes all sense.
One thing is, given the features, you select the salient features, select important features. See? A second way is, given the features, make new features that are small in number. So you do not select the features. For example, if you have 100 features, do not select, let's say, this feature and that feature and that feature. That's one way if you can do this, but this is very hard. Another way is use the 100 features and by using these features somehow make new features, let's say 10 or 15, that are not the exact features, that are not the selections of the features, that are actually made from the old features. Make new features, and those features are very, very expressive, they have very good classification power and stuff like that. So जो मैं अभी थोड़ी देर पहले बता रहा था, that is called feature selection. जो मैं अभी बात कर रहा हूँ, that is called feature transformation. So make new features given old features. By considering that when I make the new features must have this much property of classification or reconstruction or whatever. Make sense? Yes.
आपने फीचर रिडक्शन के लिए और मतलब इम्पोर्टेंट फीचर सिलेक्शन के लिए आपने एक मेथड पहले ही बताया हुआ है कि SVD यूज़ कर लो और DUV आ जाते हैं तो उसमें तो
मैं उसकी मैथ बताऊँ.
कंपोजिशन तो नहीं उसमें होती ना ये सारी.
मैं उसकी मैथ आज बताने जा रहा हूँ. That is feature transformation और selection नहीं होता.
वो सिलेक्शन
नहीं, that is feature transformation. उस दिन मैंने SVD लिखा था वो कोड में लिख के पिछले कोर्स में. आज मैं उसकी सारी मैथ बताऊँगा और उस वक्त मैंने कहा था कि इसको PCA कहते हैं. तो आज मैं PCA बताऊँगा मैथमेटिकली क्या होगा. सो ये कंप्यूटर विजन के कोर्स जो पिछले लोगों ने पढ़ा उनको मैंने PCA का कोड लिख के दिया है विदाउट टेलिंग के why it works. मैंने जस्ट बताया कि ये इस तरह से काम करता है. That's how if you transform the features in this way they have these one property without proving things. Today I will prove when I actually will drive the whole thing. Make sense? Okay, so by the way, this is also a transformation of the features. अगर ये बात से देखें, this is also transformation of the features. Yes? So let's say your original xi is d-dimensional, and let's say you have k clusters. Let's say you have k clusters and your d-dimensional data with the property that k is much lesser than d. Then your xi dash is simply k by 1. This is also one kind of transformation of the features. From the old features you get new features, and after the new features you apply linear regression. So ये जो RBF networks हैं, in particular if your dimensionality is higher than your number of clusters, then the RBF network implicitly actually do the dimensionality reduction. लेकिन वहाँ पे जो dimensionality reduction हमने की थी, अगर बाद में ऐसा भी हो सकता है कि आप original dimension 2 है और आपका number of clusters 15 है, तो फिर ये dimensionality increase भी कर देगा. Make sense? मैं सिर्फ आपको ये बता रहा हूँ कि already you have done feature transformation already. So feature transformation means given the features, come up with the new features with a particular goal in the mind. The goal might be classification, the goal might be representation. Yes, no? So those who are interested in feature selection, I recommend this paper. Study this paper. It's a very, very good paper. I read this paper. I mean, six years ago, and this I really get to know very good things about this paper. इसमें बहुत अच्छी चीजें लिखी हैं. So, but the goal today is not the selection. I'm going to use transformation. Okay, and the goal is the following. Representation objective. The objective is the following here. You have data x, which is d by n, 10 points, each with d features. Say it. You transform the data. Into x bar with the new dimension k by n. Make sense? And this k happens to be much smaller than d. Make sense? Then by representation I mean you reverse x bar and get your original x back. With this goal in mind, we are reducing the dimension by keeping in mind that we want to represent the original information. अगर इस ऑब्जेक्टिव को और से देखें तो मैं ट्रांसफॉर्म की जगह पे एक बड़ा खूबसूरत टेक्निकल वर्ड यूज कर सकता हूँ, compress.
अच्छा, decompress.
और रिवर्स की जगह पे decompress. Make sense? और यहाँ पे गोल ये है कि डेटा की डायमेंशन रिड्यूस करो, लेकिन जब भी मैं ओरिजिनल डेटा वापस रिकंस्ट्रक्ट करना चाहूँ, I can reconstruct. So this objective is representation. The data की डायमेंशन रिड्यूस करो, नए फीचर्स लेके आओ, बट वो जो फीचर्स हैं उनमें से कोई इंफॉर्मेशन लॉस ना हो. I can always recover my original data back. If that is the goal, then this dimensionality reduction, which is unsupervised, does not take any account of the labels of each feature vector. This unsupervised dimensionality reduction technique is one paradigm in which your goal is to compress and then decompress. यहाँ पे एक चीज बड़ी नोटिस करने वाली है. If k is really smaller than d, and you can compress the data into k dimensions, such that you can always decompress your data back with zero error, then obviously there are some information that is useless here. Make sense?
नहीं
You have D numbers, you have D properties of an object. And the same object description can be found by just K numbers. Which means using all of D, you are using a lot of redundant information. Maybe आप redundant information use कर रहे हैं जो 2 या 3 से मिल सकती information वही आ गई यानी आपसे कोई कह दे कि मेरे पास 2 numbers हैं और उन दोनों नंबरों का sum 7 है ठीक है तो that is one information वो 2 number let's say find out करते हैं 2 numbers का sum 7 है that's one property of the 2 numbers दूसरा हम दोनों का product जो है वो let's say 5 है let's say ठीक है और फिर आप उसके बाद क्या देते हैं उनमें से एक नंबर जो है वो 2 है उनमें से एक नंबर जो है वो तो फर्स्ट 2 प्रॉपर्टीज आप क्यों दे रहे हैं
क्या कह रहे हैं पहले में इतना ऐड करो फिर में इतना ऐड करो तो ये बन जाता है
यस सो मेरे पास एक नंबर है जो कि मेरे पास एक नंबर है जब उसको मैं 98 में ऐड करूँ तो 100 हो जाता है ठीक है और उस नंबर को अगर मैं 2 में ऐड करूँ तो 4 हो जाता है You do not need both of the information for that. That's redundant information. It's likely. Make sense? समझ आई बात? So, if a k-dimensional representation is available so that you can reconstruct with zero error, that means there is a redundant or user's information here that you can discard and still as much expressive as much representative as you were before. Make sense? Here the goal is reconstruction. वो representation लेके आए डेटा की जिससे मैं original data reconstruct कर सकूं और वो जो representation है it should be as small as possible. Make sense? तो obviously useless information discard हो जाएगी. Make sense? But the goal is reconstruction here. The other objective is classification objective. Here the goal is the following. Transform your data X और इसके साथ हम label भी लेके जाएंगे. Label भी लेके जाएंगे. And the result will be X bar and Y. That's the result. Y labels changing होंगे. This will go change. K, Y, N. And that's it. The goal is X bar and Y is much better
then next one
than X, Y for classification. Here the goal is, I mean, who cares if मैंने data reconstruct करना है? If my final goal is classification, who cares about reconstruction? Just make new features that are good for classification. And in this case, because the goal is not a reconstruction, in general you cannot reconstruct X back from this. The dimensionality reduction happens in a way that my goal is classification. I don't want reconstruction. Make sense? This is called unsupervised dimensionality reduction or representation of vector. This is supervised dimensionality reduction. We will study today one classic algorithm in this domain which is called PCA. And in the next lecture we will study one classic algorithm in this domain which is called FLD, featureless linear discriminant. Both are dimensionality reduction techniques. One is the dimensionality reduction by the hope of reconstruction. One is dimensionality reduction by the hope of classification. Make sense? So our objective today is this. Yes, no? Make sense? यहाँ पे एक सवाल आप ये कर सकते हैं कि यार ये PCA हम कर ही हुए हैं जब हमारा गोली क्लासिफिकेशन है तो why not just this one? It turns out the PCA has a very, large amount of applications in classification as well. So sometimes you just do the PCA and then those new features you use those for classification and they work very well. Sometimes you use PCA for noise removal. That I will show you later. And sometimes this PCA kind of techniques. The PCA is used as a black box and it is used to, in FLE, there are some steps that use PCA as a black box. Make sense? So this algorithm is very good to know what that is. ठीक है जी? Yes, no? by the way, one technical note. If PCA is applied for the image data in which the images are faces, and on the image data, what you do is you have faces, and then you just use all the intensity vectors and use vector x. यानी इसकी जो ये वाली इंटेंसिटीज हैं, इंटेंसिटीज वो यहाँ पर रखी, ये वाली इंटेंसिटीज यहाँ पर रखी, एक वेक्टर बना दिया. That's ठीक. If this is your training data, the training data belongs to face. Then on face training data, this PCA, this technique is called eigenfaces. If somebody of you have heard this name, this paper is from Kirk and Pentland. It's a very, very famous paper. Even in the very deep learning में face recognizer बहुत बड़े अच्छे आ गए, but this is one of the classical face recognizer that works the most. MATLAB built-in तो नहीं है, लेकिन ये, I mean, in most of the libraries जब आप जाएंगे तो this one will be there. If you apply FLD on the face data, this particular technique is known Fisher faces. Just if you want to see the papers and somewhere they write out eigenface, Fisher face, don't worry about the dimensionality reduction of face data. Make sense? You can have eigencars if you apply the PCA on cars data. You can have eigenfans or Fisher fans. Make sense? But somehow these two terms they become very much famous.
आइगन समय भी हो सकता है
जी,
आइगन समय भी हो सकता है
I can sum you okay. Yes. And by the way, this Fisher, this comes from this because this is Fisher's linear experiment. This where this eigen comes from? Because this is PCA's principal component analysis. That's the name of it. Principal. There does not seem any remote connection with eigen. I will show you where the word eigen comes from. That goes with it. Make sense? G. For the sake of simplicity, I'm just assuming for now that my original feature space is three dimensions. I will show you some visualizations here, and then we will actually the results will extend into three-dimensional and stuff. Let's say we have three-dimensional features, so which means x is 3 by n. So this is that, and several feature vectors, n of those. Make sense? That's it. Say, first of all, notice that every feature vector, it is actually a vector of three real numbers. Yes? Which means it is a point in three-dimensional space. It is just a location. That's why the feature vector is sometimes called a feature point or simply a point or a data point. Where this point comes from, if you have a vector of three numbers, there is a three-dimensional space in which it is just a location. Make sense? Which means this very first coordinate is actually this number, your orthogonal projection of this one. So the very first coordinate is x1 coordinate. The second feature is actually x2 coordinate, this length. And the third coordinate is actually zx and x3x is the coordinate. Make sense? So these are the three coordinates, which means this is if this is alpha 1, if this is alpha 2, and similarly this is let's say alpha 3, then moving alpha 1 in this direction plus moving alpha 2 in this direction. From there moving alpha 3 in this direction, you reach at the make sense? Yes. And these x's, they have these directions, the unit vectors, 0 for now, standard basis. 0, 1, 0, and this is 0, 0, 1. Yes? You can call these x's as bases as well. Basis vector. So you can call bases, you can call x's, it's up to you. Technically, in the engineers are going to call it basis. Make sense? So this is the first basis, that's the direction of it. Second basis, that's the direction. Third basis, that's the direction. Yes, no?
Yes.
Clear? If your bases are orthogonal, remember, our convention is the bases are always the direction vector, which means they are unit vectors with magnitude exactly 1. If all the basis vectors are orthogonal to each other, I mean, you pick any two of them, they take their dot product, the dot product is 0, then you can find out, अगर ये कोई point है जिसका, let's say इसका इस direction पे coordinate निकालना है, ये कोई point है, let's say 5, 3, 4. I want कि यार इस basis में इसका coordinate क्या है? How can I do that? नजर तो यहाँ पे आ रहा है, नजर आ रहा है, पहला coordinate 5 है.
Multiply
In fact,
Main shot to
dot product this
with
this. Make sense? And that gives you the coordinate in this particular direction.
Sorry.
Which actually equals to if you project orthogonally this onto this direction. So this distance from the origin, that's the coordinate. Make sense? Yes, no?
Yes.
Similarly, if you want to find out the coordinate, x2 coordinate of this point, you project this point to this, and the orthogonal projection happens if you take dot product of this and that, and which gives, if I project this on that, and this makes a 90-degree angle, then what is this distance? Yes, no? Make sense? And if you have alpha coordinate, alpha 2 coordinate, alpha 3 coordinates, then you can reconstruct the original point back by using the basis as follows. 5 times the first basis, use these steps in this direction. And by head to tail, then use these steps in this direction. And then use these steps in this direction. And you are back where you were. Make sense? Yes, no?
Yes.
Is that okay? Question? Let's say this is a vector and its direction vector is the following. Let's say A, B, C. Let's say this is the direction vector of this vector. Make sense? And I want this point का coordinate in this axis. How can I find that out? मेरे पास में है ये कोई डायरेक्शन वेक्टर कोई बेसिस है कोई डायरेक्शन वेक्टर है सही और ये डायरेक्शन वेक्टर है which means इसकी मैग्नीट्यूड 1 है मैं इस पॉइंट का कोऑर्डिनेट फाइंड आउट करना चाहता हूं इस बेसिस पे यानी जैसे x कोऑर्डिनेट y कोऑर्डिनेट z कोऑर्डिनेट है call it let's say p and find out the p coordinate of this. What should I do? All I need to find out is project this orthogonally here and find out this distance. Okay? Make sense? And this distance can be found by using the following. So A, B, C, dot product with 5, 3, and 4. That will be a number, and then that number is this. Make sense?
Yes.
Yes, no?
Yes.
Okay. If I force this point to be represented on this line, then this is the best representation. This is the representation to the minimum error. Make sense?
Yes.
Yes, no?
Yes.
Oh, I actually, if I force this point to be represented elsewhere on this line, like here or here, these are bad representations of this point. For this point, on this line, this is the best possible representation. Make sense? Yes, no?
Yes.
let's say this is my data, again 3D. Yes. Each data point has 3 coordinates. X1 coordinate, X2 coordinate, X3 coordinate. Yes. Each actually feature vector has 3 features. Yes. Let's say the whole data lie in a plane. Let's say the whole data lie in a plane. Which means if you plot the data and see the 3D space, and let's say this is the 3D space and that is in your hand, let's say. Let's say you are a real person, you're controlling the 3D space, okay? And then you move the 3D space here, here, here. And this data, which is the data, it always look like that it is in a plane. There is a plane in which all that data lie in. Yes? You can always find out a plane in which this data, that's it. Make sense?
Yes.
Yes.
This means in 3D I can always find a plane जिसमें सारे सभी parts exist करते हो.
No. All am I saying? This is data, the structure of the data is in a way that it lies in some plane. This is not true that you come up with, actually if you have 4 points, you can make them to not lie in a plane.
Yeah.
Make sense?
Yeah.
अगर 3D से ऊपर जाएंगे that would be a hyperplane. अभी चूंकि 3D के अंदर the plane is just a plane. If the original dimension is 4D or 5 or 60, then we call it a hyperplane. लेकिन visualization simple करने के लिए I'm assuming that original feature space is 3D, and let's say data है इस तरह का कि वो एक plane में lie कर रहा है. Let's say अगर ऐसा है तो what can we achieve मैं ये बात करने जा रहा हूँ. Make sense?